Okay, section 4.3 is about acid-base reactions, and this is a very important class of reactions. So let's review what a strong acid is. A strong acid is an acid that ionizes completely in solution. A strong acid is a strong electrolyte. So when you have a strong acid in solution, you only have the ions that it forms. You don't have any of the intact molecules. There are 7 strong acids according to this textbook. You just memorize them, and those are the strong acids. Anything not on the list that's an acid is considered a weak acid. Weak acids are those that only ionize a little bit in solution. And then there are the strong bases. So the strong bases are the hydroxides of the group 1A metals and the heavy group 2A metals. The heavy group 2A metals are the ones at the bottom of the periodic table. So that's calcium, strontium, and barium. The group 1A metals are all soluble in water because of that rule. All group 1A ionic compounds are soluble. Calcium, strontium, and barium hydroxide are not considered completely soluble, but they are slightly soluble, and so they are still considered strong bases. Strong bases also dissociate completely. They completely form ions in solution. So they are also strong electrolytes. There are different definitions of what is an acid and what is a base. One of the earlier definitions is the Arrhenius acid, and this is named after the scientist who used it, Svante Arrhenius. An Arrhenius acid is a substance that ionizes in water to produce hydrogen ions. That's the definition we've been using. An Arrhenius base is a substance that ionizes or dissociates in water to produce hydroxide ions. So if it makes hydroxide ions, it's a base. If it makes hydrogen ions, it's an acid. One of the limitations to this definition is that it only applies to aqueous solutions, which is fine for Chem 101P, fine for Chem 1A, but there are a lot of reactions that occur in other solvents, and this does not define what's an acid or a base. So the more inclusive definition is the Bronsted or Bronsted-Lowry definition. A Bronsted acid is a proton donor, and a Bronsted base is a proton acceptor. Now, that seems to be like a completely different definition than the one according to Arrhenius. And yet, the Bronsted acid and base definitions do include everything that is defined as an acid or base by the Arrhenius definition. So let's look at that. So when we talk about a proton donor or a proton acceptor, we're familiar with the proton as being the subatomic particle in the nucleus. But let's think about what is a hydrogen ion. And before that, what is a hydrogen atom? A hydrogen atom. How many protons does a hydrogen atom have? One. Its element number 1, its atomic number is 1. That tells us that a hydrogen atom has 1 proton. If it has 1 proton, how many electrons does it have? 1. 1 proton and 1 electron. So if we make that into a hydrogen ion, H+, ions are formed by gaining or losing electrons. So the hydrogen ion still has 1 proton. Because of the positive charge, we know that it's lost 1 electron. It only had 1 electron to start with. So really, a hydrogen ion is a bare proton. The most common isotope of hydrogen does not have any neutrons. And so really, a hydrogen ion is the same thing as a proton. Does it seem a little bit odd that you would have just protons floating around in water? Yeah, it does seem a little strange. Well, the protons don't actually float around in water, and we'll get to that in a minute. But when we say a proton donor or a proton acceptor, we can think of that as being a hydrogen ion. A hydrogen ion is essentially the same as a proton for this context. So if we look at ammonia, ammonia is NH3. When we put NH3 in water, the ammonia accepts a proton from the water molecule. So we've got the picture up here, but we can also draw this with symbols. We can think of water as being a hydrogen attached to hydroxide, or thinking of it in ionic terms, it's a hydrogen ion and a hydroxide ion. So if the water donates the hydrogen ion to the ammonia, ammonia then accepts the proton. A base is a proton acceptor. And so this is acting as a base. And we get the ammonium ion, and then what's left after the water loses a hydrogen ion, it's the hydroxide ion that's left. So the Bronsted-Lowry base definition says that ammonia is a base because it accepts a proton. The Arrhenius definition says that ammonia is a base because when you put it into water, it ionizes and forms hydroxide ion. Okay? But this definition works if you don't have water as well. It will work in other solvents. Any questions about that? I am not going to ask you to distinguish between the Bronsted definition and the Arrhenius definition. I see no point in that. I do want you to know that you can define an acid as something that forms hydrogen ions in solution, or you can define it as something that donates hydrogen ions. And with a base, it's something that forms hydroxide ions in aqueous solution, or something that accepts a proton. Hydrofluoric acid, obviously from its name, this is an acid. This is an acid by both of the definitions. We look at HF, and that's a weak acid. And so here we're using the arrows pointing both ways, which tells us this does not go completely to the hydrogen ion and to the fluoride ion. It does not ionize completely. There's a lot of HF molecules still present. It just goes this way a little bit. But it forms hydrogen ion. Well, this hydrogen ion is being donated. We can't really see how it's being donated, the proton donor, in this form. So then we have to talk about, well, what about this aqueous proton? I think of that aqueous proton, that hydrogen ion, as being a tiny baby, newborn baby. Newborn babies do not go outside by themselves. They don't go to the store, they don't go for a walk, they don't go play in the yard, right? They're always carried by someone else because they're too small. This proton, I've told you, hydrogen is like the baby brother of the element family, right? Well, this proton, this hydrogen ion, is even smaller. And so it's too small to go out by itself. It does not exist as an isolated species in solution. There are no hydrogen ions in the solution. It is hydrated. It is actually sitting on a water molecule, and it forms this hydronium ion. So I think of the hydronium ion as being someone holding the baby. So here we have the hydrogen ion, and in an aqueous solution, you got water molecules all over the place. The water molecule is kind of like the babysitter. And this hydrogen ion, too small to be out alone, is going to attach itself to the water molecule. And that's where we get this hydronium ion, H3O+. And that was on your list of polyatomic ions to memorize. So H3O+. So when we think about the hydronium ion, we think about putting hydrofluoric acid in water. The hydrofluoric acid is going to donate this hydrogen ion to the water. Donating a proton Donating a hydrogen ion is the definition of an acid. So this is acting as an acid. Here the water is accepting, so actually here the water is acting as a base, and it forms the hydronium ion and the fluoride ion floating around by itself. Any questions? So what is often confusing to students, we use both of these. We talk about hydrogen ions and we talk about hydronium ions, and we use these two different formulas. They actually refer to exactly the same thing, because you cannot have a hydrogen ion by itself. In fact, all ions are hydrated in solution. We went over that very briefly. The water molecule is slightly positive on its hydrogen end and slightly negative on its oxygen end. And so there are attractions between these partial charges on the water and the charges on the ions. It's just that with the hydrogen ion, it goes a little further and it actually becomes more attached to that water molecule. So I think of the water molecule as being the babysitter and the hydrogen ion as being the baby. And so in these acid-base reactions, what's happening is the baby is just being passed back and forth to people. The person accepting the baby is the base, and the person handing off or donating the baby is the acid. So here, HF is donating this hydrogen ion to the water. This is acting as an acid. If we go back to this slide, now the ammonia is accepting a hydrogen ion from the water. It's accepting, it's acting as a base. So it's all about handing off the hydrogen ion. Does that make any sense? It's kind of a, I just feel like I'm springing stuff on you. I'm sorry. Most of the strong acids, in fact all but one of them, are considered monoprotic acids. So if we look at this word, mono is a prefix meaning one, and protic refers to protons. So Bronsted definition, acid is a proton donor. Well, a monoprotic acid has one proton that it can donate. One hydrogen ion can be donated. Sulfuric acid, H2SO4, is a diprotic acid. It's two. The prefix di means two. Diprotic, it has two protons to donate. So every molecule of H2SO4 can donate two protons. And then you have also triprotic acids, much less common. Can you think of a triprotic acid? It's going to have to be H3 something. Phosphoric acid, H3PO4. It has three hydrogen ions that it can donate. And then just to round things out here, we use the term polyprotic to refer to either diprotic or triprotic acids, just something with more than one proton. So I mentioned that sulfuric acid is the only strong polyprotic acid. And it's actually only strong in its first ionization. So what happens is that these ionizable hydrogens, these protons that can be donated, they don't just all fall off at once. It doesn't donate all of them at one time. It hands them off sequentially. So the H2SO4 will donate one proton. So here's the proton. We're just writing it as H plus here. But we understand when we see this that that's actually on a water molecule. It's a hydronium ion. It just makes our chemical formula, our chemical equations much simpler if we don't have to throw all the H2Os in there. So it donates this one proton, and then what's left is the hydrogen sulfate ion, HSO4 minus 1. This is a strong acid. All of the first hydrogen ions come off. So in aqueous solution, you don't have any H2SO4 molecules hanging around. But this HSO4 minus ion, this hydrogen sulfate ion, also has a proton here that can be donated. This can also act as an acid. but it does so as a weak acid. So the hydrogen sulfate ion can donate its proton, and what's left then is the sulfate ion. But this has the double arrow. This is a weak acid, and this only happens to a small extent. So there's very little actual sulfate ion in this solution. It's almost entirely hydrogen sulfate. Other diprotic acids, oxalic acid, it's the only one I can think of off the top of my head, and the triprotic acids like citric acid and phosphoric acid, those are weak in all of their donations of hydrogen ions. Looking at the bases, some of the strong bases, those ones that are the heavy group 2A metal hydroxides, produce more than one hydroxide ion for each formula unit of the base that dissolves. So if we look at barium hydroxide, its formula is BaOH2. So we can tell from the formula there's 2 hydroxide ions in each formula unit of this. So when barium hydroxide solid dissolves in water, it forms a barium ion and 2 hydroxide ions. Barium hydroxide is an ionic compound. When it dissolves, it ionizes completely. There are some ionic compounds that don't dissolve in water, but there are no ionic compounds that are weak electrolytes. They either dissolve and ionize completely, or they don't dissolve. They're not like the acids that can be weak or strong. So those are called dibasic bases because they give off 2 hydroxide ions. And monobasic bases would be things like sodium hydroxide. They only make 1 mole of hydroxide per mole of compound. So sodium hydroxide, when that dissolves, you get 1 sodium ion and 1 hydroxide ion. That's a monobasic base. So acid-base neutralization. This is a type of reaction. A neutralization reaction or an acid-base neutralization reaction is a reaction between an acid and a base. And when this happens, the products are always water and a salt. A salt always reminds me of the word assault, where you're attacking someone. And this, I have to show you this because every time I say assault, this is what I think of. Here's an assault rifle. It's made out of salt. Salt, to chemists, is basically an ionic compound. It's an ionic compound made up of the cation from a base and the anion from an acid. So you'll often hear people refer to any ionic compound as a salt, but technically there are some ionic compounds that are not salts. But in a neutralization reaction, what we end up with is salt, not necessarily sodium chloride, but some ionic compound, and water. Neutralization reactions are a type, a subclass of the double replacement reaction. And so we can predict the products in the same way. So I always like it when you can learn one method and it applies to lots of different things. So we looked at how to predict products of precipitation reactions. You've got 2 ionic solutions mixing together, and we just swapped the ions and looked at what we had. We can apply that same idea to neutralization reactions. And we'll look at that in a minute. Actually, yeah, I need an equation here. Okay, so stuff missing from the slide. So let's look at something like sodium hydroxide plus hydrochloric acid. We've got a strong base, and we've got a strong acid. And we can predict what the products are doing the same thing that we did for the precipitation reaction. Let's look at the 2 ions that each of these forms and then switch the partners. So sodium hydroxide dissociates to form sodium ions and hydroxide ions. Hydrochloric acid is a strong acid. it ionizes to form hydrogen ions, which we understand are riding piggyback on a water molecule, and chloride ions. And then if we switch ions and put the hydroxide with the hydrogen and the sodium with the chloride, then we've got sodium ion with chloride ion, and we've got hydrogen ion with hydroxide ion. And then we look at the charges and we stick them together. So NaCl, and then is that a soluble compound or not? Yes, it is. Because the first thing in those tables was group 1A compounds are soluble, no exceptions. Sodium is group 1A, sodium chloride is soluble. So that would be aqueous. And then when we stick H plus and OH minus together, if we do that kind of without thinking very much, just sort of by rote, we have a +1 ion and a -1 ion. And so if we stick them together, we get HOH. Huh. That looks kind of funny, doesn't it? Yes, somebody smiled. That, huh. You could pronounce that, huh? Or whole or something. Anyway, normally we write the two H's together, right? That's just water. When a hydrogen ion and hydroxide ion run into each other, they're attracted to each other, they stick together, and they actually are just a water molecule. So instead of writing it like that, we write H2O. Well, what would the state symbol for water be? Liquid. It's not dissolved in itself, right? It's not aqueous. And we're assuming room temperature, and so the state would be water. I'm sorry, the state would be liquid. Now, let me see here. Let's get rid of this mess down here. I meant to do this as an example before we did the more interesting example. If we were to write an ionic equation for this, remember an ionic equation, we take anything that's a strong electrolyte and we separate it into the ions. Because sodium hydroxide is a strong electrolyte. It separates completely into sodium ions and hydroxide ions. In the ionic equation, we're going to write the things as they actually are in the solution. So there are sodium ions, and they are separate from the hydroxide ions. And then this is a strong acid. Strong acids ionize completely. There are no HCl molecules in this solution. There are just hydrogen ions and chloride ions. And then we look at the products, and here we have a soluble ionic compound. That's a strong electrolyte. So that's going to be found as sodium ions and chloride ions. To make the ionic equation, do we take a liquid and separate it into ions? No. The only things that get separated into ions have HU as their state. If it's got liquid, solid, or gas, you just copy it down as it is. So then we've got water, because water is present as individual molecules. Then to make the net ionic equation, remember, we cross out the spectators, right? So what are the spectators here? Well, we've got sodium ion as a reactant and sodium ion as a product. Nothing happened to the sodium ion. It's just standing around watching what's going on. And then we've got chloride ion that's also just hanging out there, not doing anything. And what's left? What's left is this. H plus OH minus giving water. This net ionic equation is common to many acid-base neutralization reactions. The exceptions would be if you have a weak acid or a weak base, because then those in the ionic equation would not be separated into ions. Or if by chance you ended up with a salt that was not soluble, and that could happen. Like if you reacted barium hydroxide with sulfuric acid, you'd end up with barium sulfate as your salt. It's not soluble. But most neutralization reactions have this common net ionic equation. Any questions? So let's do a couple of examples. Write balanced molecular and net ionic equations for the following neutralization reactions. So here, sulfuric acid and potassium hydroxide. We have to get the formulas correct for each of these compounds. And so it's best, I think, to show the ions with their charges. So sulfuric acid is an acid that contains oxygen. I know that because it doesn't start with the prefix hydro. If it was hydrosulfuric acid, then it would not have oxygen. Because it doesn't start with hydro, it's got oxygen. And that's where we use that sentence, Rick ate him before he could bite us, right? Sulfuric, ick and ate go together. This comes from the sulfate ion. So sulfuric acid has sulfate in it. Sulfate, and then because it's an acid, the cation is going to be hydrogen ion. Potassium hydroxide. We write the formula for potassium. Potassium is K. It's in group 1A, so the charge is +1. Hydroxide is OH minus because you memorize it. And then we combine the ions to make the formulas for the compounds. Sulfate has a -2 charge, so it needs 2 hydrogen ions. So we get H2SO4, and that's going to be aqueous, plus, here we've got a +1 and a -1. We just need one of each, KOH. Is that soluble? Yes. It's a group 1A compound. It's soluble. And then this reacts to form. Now we swap swap ions to find the products. So I'm going to try the potassium with the sulfate and the hydrogen ion with the hydroxide ion. So here we're going to have K plus with SO4 2 minus, and we're going to have H plus with OH minus. I write the formula for the potassium sulfate by looking at the charges. 2 minus and +1 tells me it must be K2SO4. Is it soluble? Yeah, it is, because all potassium compounds are soluble. And then H plus and OH minus, that's water, H2O, and its state would be liquid. So there's a molecular equation. Is it balanced? No. If you've got monoprotic acid and monobasic base, then all the coefficients are going to end up being 1. If you've got a polyprotic acid or a dibasic base, then you're going to have to balance it. So H2SO4, this is diprotic. It forms 2 hydrogen ions. Those 2 hydrogen ions, one of each goes to a water molecule. And then this is a monobasic base. If you're just balancing without thinking about the acids and the bases, here you've got K2, and there you've only got 1 K. And so we need a coefficient of 2 in front of the hydroxide. And then that gives us 2 hydroxide ions and 2 hydrogen ions, so that's going to make 2 water molecules. So there's our balanced chemical equation, the molecular equation. I'm going to erase this because I don't have enough room on my slide. On a piece of paper, you would just move down. So it doesn't say we have to write the ionic equation. It just wants the net ionic equation. But let's do the ionic equation anyway, which is kind of just rewriting what I erased just now. So this is a strong acid, right? And so that will ionize completely. We're going to ignore the second part of the ionization being weak because that just gets way too complicated. I shouldn't have done this one as an example, but oh well. So we're going to write this as 2H plus aqueous and sulfate aqueous. And then we have 2 potassium ions and 2 hydroxide ions. And then over here, we're going to separate the K2SO4 because this is aqueous. It's an ionic compound. And so that gives us 2 potassium ions and 1 sulfate ion. And then the water molecules do not get separated because those are liquids. It's a molecular compound, H2O liquid. So there's our ionic equation, and then to do the net ionic equation, we cross out the spectators. So spectators, we got sulfate on both sides, and we've got 2 potassium ions on both sides. And copying down what's left, we've got 2H plus and 2 hydroxides. And on the product side, I've got 2 water molecules. What's wrong with that equation? You don't need the 2's. Strictly speaking, it's balanced, but it's weird, right? Mastering chemistry, you're not using mastering chemistry. Connect would probably not like this because you could simplify this and get rid of the 2's. So I'm just going to get rid of the 2's. I'm dividing all the coefficients by 2, so I get 1's to get things as simple as possible. And there's that very common net ionic equation, H plus OH minus gives water. Any questions? Let's do acetic acid and calcium hydroxide. What's the formula for acetic acid? What does it come from? Acetate. So that comes from the acetate ion. So acetate is C2H3O2 minus. Why is that acetate? Because that's what we decided to call it, right? And then there's going to be H plus. So this has a -1 charge. It only needs 1 hydrogen ion. This sulfate had a -2 charge. It needs 2 hydrogen ions. So acetic acid is just HC2H3O2. Now, that might look strange to you as well. Why is this hydrogen out in front and these hydrogens stuck in the middle? This hydrogen that's written in the front, that's the ionizable hydrogen. That's the proton that's donated when this goes into solution and acts as an acid. These other 3 hydrogens don't do anything. They stay there. So that's why we write it that way. Calcium hydroxide. Well, we've got calcium ion. Calcium's in group 2A, 2 plus ion. Hydroxide is OH minus. We look at the charges. That's going to be CaOH2. Now this question that I made up at 2 o'clock this morning is very vague. It doesn't specify are these solutions or not. We're going to assume that they are aqueous solutions. And calcium hydroxide would dissolve in water. So that's reasonable. What are the products going to be? a salt and water. Well, what's salt? Well, it's the cation from the base and the anion from the acid. So calcium acetate. So we got the calcium ion and the acetate ion. And we look at the charges and we see that we need Ca, C2H3O2, 2. Is that soluble? Yes. The first rule, remember I said if you just memorize the first 2 rules, that'll cover a lot of things, right? The first rule of solubility is that all group 1A compounds are soluble and all ammonium compounds are soluble. The second rule had nitrate and acetate and chlorate and perchlorate. All of those are soluble, no exceptions. So this being an acetate compound, it is soluble. So AQ. And then the other product is water. And then we need to balance this. Now this gets a little messy looking with all the H's and O's all over the place. So if you wanted to do them as elements, that would be fine. That always works. It's faster if you can look at them as polyatomic ions. So here I have 1 acetate ion, and over here I have 2 acetate ions. So that tells me I'm going to need a 2 in front of acetic acid. And here's the hydroxide. I've got 2 hydroxides and 2 hydrogen ions, and that tells me I'm going to get 2 water molecules. And I have 1 calcium here and 1 calcium there. So you might arrive at this balanced equation a little bit differently, but we should all end up with the same balanced chemical equation. Any questions? Okay, separating this into ions, I'm going to just cheat a little bit and not write everything out necessarily. So let's think about this. Okay, here we have an acid. It's aqueous. If we're writing the ionic equation, is acetic acid a strong acid? Is it one of the 7? No, it isn't. The strong acids are hydrochloric, hydrobromic, hydroiodic, chloric acid, perchloric acid, nitric acid, and sulfuric acid. Acetic acid is not on the list. So then this does not get separated into ions because it is predominantly present as intact molecules. So I'm going to erase this here because that's not going to form ions. And then over here, would we separate calcium and acetate? This is an aqueous compound. Yeah, it's an ionic compound. The only aqueous things you don't separate are weak acids or weak bases. So this would be separated into its ions. Would we separate water into ions? No, because it's a liquid. So these are the ions present, and then we're going to have water, and we're going to have acetic acid. So we only have 1 spectator ion here. The calcium is a spectator. So the calcium is going to be a spectator on both sides. So then the net ionic equation is this weak acid plus how many hydroxides? Two of them. So in this balanced molecular equation, there was 1 calcium hydroxide. We're not writing the calcium down because we determined that was a spectator ion. But when this ionizes or dissociates, it forms 2 hydroxide ions. And then over here, the calcium acetate, we're not writing the calcium because that was a spectator ion, but we have 2 acetate ions. And then we have 2 water molecules. So I was keeping track of balanced things as I was writing down my ionic equation. You can also just write the ions down and then balance it afterwards. Yes?
Why do we keep acetate?
We keep the acetate here because there's no acetate ion over here to cross off. This is a weak acid, and so it only ionizes partially. Yeah.
If there was no 2 hydrogens in the front of that in the beginning,
Mm-hmm.
would you be able to cross it off? Or you still would be able to cross it off?
Yeah, if this was acetate instead of acetic acid, then we could cross the acetates out.
Okay.
But because it's a weak acid, we don't do that.
And if it didn't have those, it wouldn't be weak acid anymore?
Well, we're looking at the molecular equation to start with, and this is acetic acid. Acetic acid is a weak acid because it's not on the list of strong acids. So there's nothing you can do to it to make it a strong acid. The other thing we need to do here is we look and we see that all of these coefficients are 2s. And so we should get rid of those because we want the lowest coefficients that we can have. So this example does not yield the same net ionic equation because this is a weak acid, not a strong acid. Any questions? Okay, here's the example from your textbook. Milk of magnesia is an over-the-counter laxative. It's a mixture of magnesium hydroxide and water. Magnesium hydroxide is insoluble in water. And so milk of magnesia is made as a suspension rather than a solution because the magnesium hydroxide doesn't dissolve in water. So they treat it so that it's a suspension, and that's why it looks like milk, and so they call it milk of magnesia. It looks like milk. Doesn't taste like milk, don't pour it on your cereal. But it looks like milk. Because the particles are larger and they block the passage of light, and so it's a suspension. What happens when an acid such as hydrochloric acid, which is the main acid that's in your stomach, is added to the milk of magnesia, the suspended magnesium hydroxide dissolves. And when it dissolves, you get a clear, colorless solution. Now you have a solution and everything's dissociated. So this is asking us to write and balance the molecular equation and then give the ionic and net ionic equations for this reaction. Well, we need some more room here. I should have made another slide, but I didn't. Oh, that's too small. That's better. So they're saying we've got magnesium hydroxide, which is insoluble in water, so that's a solid, reacting with HCl, which is aqueous. And they're asking for the molecular equation, the ionic equation, and the net ionic equation. We were given these formulas. So how do we predict what the products are? We can look at this and say, that looks like a base. This is not a strong base because it's not soluble, but this has hydroxide ions in it. And this is an acid. We recognize that because it starts with H. This is an acid-base neutralization reaction. We don't have to recognize that to be able to do this problem. You just treat it like a double replacement reaction, swap ions, and put them back together and see what happens. So let's look at the ions that are present in magnesium hydroxide. Well, it's magnesium and hydroxide. So we've got Mg, 2+, and we've got OH minus. And then in the hydrochloric acid, we've got hydrogen ion and chloride ion. And then we switch partners here. So we're going to put the magnesium with the chloride and the hydrogen with the hydroxide. So I'm going to write them over here, magnesium and chloride and hydrogen ion and hydroxide ion. And hopefully by now we're learning to recognize that hydrogen ion and hydroxide ion, when you put those two together, you get water. Magnesium and chloride, we're looking at the signs, the charges, +2 and -1. So that tells me I need 2 chloride ions. Let's try that again. 2 chloride ions for every magnesium. Is that compound soluble? The third line in the table was that the halides, chloride, bromide, iodide, are soluble except with silver, mercury 2, and lead 2. Not one of the exceptions, so this is soluble. So for the chlorides, iodides, bromides, the exceptions are very small. So, you know, if you don't remember those, a good guess would be soluble. So there we have our products, and then we need to balance the equation. Well, here's 1 magnesium and 1 magnesium. These guys get kind of messy, the hydrogens and the oxygens. Let's look at chlorine. Here's 1 chlorine and there's 2 chlorines. So I need a 2 in front of the HCl. And now let's look at the hydrogens and the oxygens. Here I've got a total of 2 oxygens. And over on the right, I only have 1. So I need to put a 2 in front of the water molecule. Now I've got 4 hydrogens here, and I've got 2 there and 2 there, a total of 4. So everything's balanced. So there's my balanced molecular equation. Any questions? Now we need to write the ionic equation. Writing the ionic equation, we're going to take anything that's aqueous and look at it. Well, MgOH2 is a solid. Yes, it's an ionic compound, but it's insoluble in water. So this is going to be sitting there as a solid. So we just copy that down. MgOH2, solid. Here we have an aqueous compound. We need to think about this a minute. Is it an acid? Yes. Is it a strong acid? Yes. Hydrochloric, hydrobromic, hydroiodic acids are all strong acids. So it's a strong acid. That means it does separate completely into ions. So then this is going to be 2H plus and 2Cl minus. If it was a weak acid, we would copy it down as is. Then looking at the first product, we see aqueous as the phase. This is an ionic compound. It's not an acid. Acids are the only ones you have to worry about. Ionic compounds that are aqueous always get broken into ions, separated. So Mg2 plus aqueous plus 2 chloride ions aqueous. Oops, running out of room. And then the water is a liquid, not separated into ions. Any questions? That's the ionic equation. Yes?
Is the reason you didn't separate the magnesium hydroxide because it's a solid?
Yes. Yep, I'm not going to separate that one because it's a solid. What we're trying to do with the ionic equation is show how most of these things actually are in the solution. Because magnesium hydroxide doesn't dissolve in water, we don't see magnesium ions and hydroxide ions. We see intact lumps of magnesium hydroxide. The hydrochloric acid is a strong acid. Strong acids ionize completely. So it completely goes into hydrogen ions and chloride ions. Soluble ionic compounds are completely ionized. Magnesium ions and chloride ions. But this is a liquid. If it's a liquid, solid, or gas, don't break it apart. Water is present predominantly as water molecules. So what do we do to make this into a net ionic equation? Cross out the spectator ions. You guys awake? So the spectators would be the chloride ions. We're crossing them out and not including them in the equation because they're not doing anything. They're just standing around and watching. Are there any others? No. What we're looking for is something that is the same on the reactant side as it is on the product side. So 2Cl minus aqueous is exactly the same as 2Cl minus aqueous. So we just cross them off. Those are the spectators. Once we get rid of the spectators, you just copy down everything that's left. So MgOH2 solid plus 2H plus aqueous forms Mg2 plus aqueous plus 2 H2O liquid. Check the coefficients, make sure that you can't simplify them. Here we can't, we've got 1s and 2s. There's our net ionic equation. This is the same process that we used for the precipitation reactions. And those are on the exam that we're going to start in just a few minutes. So we just had a little review of how to write net ionic equations. Any questions? That's the end of that section.